Here's the solution to problem 9 for the final exam review. Okay, in this problem, we're looking at the continuous time domain, the S domain, and we just are asked to do several things that I want you to be able to do. So the first thing is to find the transfer function, and I think we've done this enough to realize that we can just write down by inspection the transfer function, h of s, since there's just x of t, no derivatives of x, this would just be a 1 on the top. And then every time we see a derivative, we put an s. So there's a second derivative, so s squared, plus 7, first derivative, so we put the s, and then 12y with no derivative. So there we are. There's part 1, the transfer function. Part 2, we're looking at finding the impulse response. So, of course, impulse response is where we let x of t equal delta of t, and when we take the Laplace transform of that, we get 1. Okay, so to get the impulse response in the time domain, we just have to take the inverse Laplace transform of h of s. So let's get started with that. So 1 over s squared plus 7s plus 12, we factor that and we get 1 over s plus 4 and s plus 3. And you can write that in terms of a partial fraction expansion, where we know that a, using the cover-up method, the root for the a term, s plus 4, is s equal minus 4, so I cover that up and plug in minus 4 to what's left, and I get minus 4 plus 3, so a would be negative 1. Okay, doing the same thing for b. Okay, for b, we'll use a different color, use purple. The root occurs at s equal minus 3, so I cover this up and plug in what's left. Negative 3 plus 4 is 1. So 1 over 1 gives me b equal 1. So from that, I can write down h of t. H of t is going to be minus e to the minus 4t, using Laplace transform tables. Okay, minus e to the minus 3t, and in this class, we've always assumed t is greater than or equal to 0. All right, so there's the solution to part 2. Okay, so part 1 is here, and part 2 is here. This is the solution to the third part of problem 9. In the third part, you're looking at the step response, so we know that x of t is u of t, and so that means x of s is 1 over s, and since y of s is h of s, x of s, we can write down the Laplace transform of y. It would be 1 over s times h, which is 1 over s plus 3, s plus 4. So I'll leave the partial fraction details to you, but this becomes 1 over 12 divided by s plus a negative 1 over 3 divided by s plus 3 plus 1/4 over s plus 4. You know how to do the partial fraction expansion. There's the answer. Okay, so the next thing is it's important to write down the time domain answer. So in the time domain, this is 1/12 minus 1/3 e to the minus 3t minus 1/4 e to the minus 4t for t greater than or equal to 0. Okay, so there is the solution to part 3. Okay, then we're going to do parts 4 and 5, which is the pole zero diagram and system stability. Okay, so when you talk about BIBO, we were talking about the stability of a system. So we look at the poles and zeros of the transfer function. Okay, in this particular case, there are no zeros, no finite zeros. So we know we have a pole at -3 and another pole at -4. So there's the pole zero diagram. And then we also know that this is the left half plane and that all the poles are contained within the left half plane. Which implies that the system is BBOH stable. Okay, so that's parts 4 and 5. Okay, moving on to part 6. In part 6, you're given x of t is equal to 4 cosine 2t. And what's important here is we ask for the steady state solution, not the total solution. So you don't have to do the full up Laplace transform inverse. You can go with just the solution to the particular solution, which is straightforward to get by identifying x of t in the form of x e to the st. So we've done this all semester where we said in this case x would be 4 and s is j2. Okay, so j times the frequency. All right, from there we know that cap y is h of s evaluated at s equals j2 times x. If I put this in radian mode in my calculator and plug this in, I get the answer looking like 0.248 e to the j minus 1.0517. So that tells me a lot. All right, it tells me that the steady state solution for this system for x equals 4 cosine 2t is 0.248. I started with cosine, I stay with cosine. The frequency doesn't change, and I have a phase shift of minus 1.0517 radians. Okay, so I've had this question come up a couple of times. If you use the e to the j function on your TI-89 calculator, it's important for this to be in radian mode. Okay, otherwise you get a domain error. Okay, e to the jx, I would say.